Sahana Vasudevan, sorry, and she will talk about triangulated surfaces in modular space.
Thanks for the introduction and thanks for the invitation to speak here. So let me start by defining what is a triangulated surface. So we glue T number of unit equilateral triangles to form a compact genus G surface. And viewing each triangle as embedded in the complex plane, we have a complex structure on the surface, which is preserved by the gluing and extends over the vertices, which are a discrete set of points. And such a surface we call a triangulated surface. So we get a Riemann surface this way. And to be able to do this gluing process, we need to have G at least T. And we'll also assume that G is at least 2. So in this situation, it's equivalent to think about Riemann surfaces, hyperbolic surfaces, and smooth projective algebraic curves. So given by polynomial equations, hyperbolic here means curvature is -1. So in particular, such a surface has a unique conformal hyperbolic metric. And we let comp GT, this is going to be the set of T triangulated genus G surfaces. T triangulated means there are T number of triangles, and this is up to combinatorial isomorphism. In general, feel free to interrupt me if there are any questions. Okay. So in the context of metric geometry, Brooks and Makover started the study of triangulated surface in the large genus setting. So in particular, they asked the following question, which is, what are the geometric properties of a random surface in comp GT as and here there are 2 variables, and in particular we ask this question when G goes to infinity and T goes to infinity proportionally to G, so that T is actually 4G. Or T grows like close to 4G.
When you say random, is it each the same weight, or did you
yes.
one over?
Yes, you pick uniformly. Yeah. So this is for fixed G and T, this is a finite set, and you just pick uniform. Okay, so what does geometric property mean? This is with respect to the hyperbolic metric. Okay.
What do you mean more specifically? Sorry, what do you mean more specifically geometric?
Yes, I will.
Okay.
Right. Okay. So for instance, the probability that the shortest geodesic is, so there exists a constant such that this tends to 1 as g tends to infinity. And there is another constant such that the probability that the diameter is less than that also tends to 1 as g tends to infinity. And similarly, we have result for the eigenvalue of the Laplacian, first eigenvalue of the Laplacian, and the Cheever constant. Okay.
Could you remind me what the Cheever constant
Yeah.
is? I know.
Yeah, so roughly speaking, it measures how difficult it is to cut the surface into 2 pieces of roughly equal area. So if you want to precisely define, you can write. So you take in-forward curves or a system of curves dividing S into pieces A and B, and of the quantity length over minimum. Okay, so the intuitive notion is just, it measures how hard to cut the surface into 2 pieces of roughly equal area. Okay, so so this was proved by Brooks and Makover. But there is another question that, yeah.
Does it connect it together?
No, I think it can be disconnected. Yeah. Okay. So you can ask the similar question for not just these discrete set of surfaces, but all hyperbolic surfaces. So I'm going to write a new question in pink. And now if I want to pick a random hyperbolic surface, I need to figure out how I'm going to define what is random. And so this is going to be with respect to so it's okay if you don't know what is Wave-Peterson measure, but basically there's a reasonable way of picking a random hyperbolic surface of genus G. And then you can ask the same question. So what is the probability the shortest geodesic will be greater than a particular constant, and so on. And basically, you get the same results, except this one is going to be greater than 0, but the others, you get the same results. Of course, your constant situation might be different, but yeah. And this was proved by Mirzakhani.
One is false in the first part.
Yes, in the hyperbolic situation, the this does not tend to 1. It tends to something like a constant, or it tends to a positive thing, but not 1. Okay. So let me say a little bit about the proofs. So the proofs of this statement and this statement, they're very different. This one involves reducing these sorts of questions to studying cubic graphs. So cubic graph is like dual to a triangulation. And in this situation, you can understand the hyperbolic metric on your triangulated surface by looking at the corresponding dual cubic graph. And so this reduces to some set of combinatorial or probabilistic problems, and that's how Brooks and Makover's proof goes. Whereas Mirzakhani's results, they were proved by doing dynamics on moduli space. But the upshot is that there are many questions of this nature that you can ask for triangulated surface, and then similar question you can ask for a random hyperbolic surface, and then you get some basically similar answer. So you would like to understand where triangulated surfaces are distributed among all hyperbolic surfaces. So maybe let me first make or write down what is moduli space.
Where does the assumption here about from Z comes from?
This one?
Yes.
Yeah. So this is somewhat probabilistically natural. So if you just glue T triangles and you condition that you should get a connected compact genus G surface, the expected genus is going to be T over 4. And geometrically, this is a situation where you have like very few vertices with very large degree in your triangulation. And that is why in this situation, it's easy to visualize the hyperbolic metric, because in general, if you have a triangulated surface, it's hard to write down the conformal hyperbolic. Okay. So let mg equal moduli space of genus G hyperbolic surfaces. This is a 3G minus 3 dimension orbifold over C. If you don't think about orbifolds, you can just think about like complex manifold with some cone points. And so in particular, the points of MG are hyperbolic surfaces of genus G up to isometry. Okay, and now we have the question, which is where does COM GT, our discrete set, lie in MG quantitatively? But to make sense of this question, I have to define what this means. And so I have to define a metric on moduli space. And then I want to say within a ball of that metric, how many of these surfaces lie in that ball. So let me put a metric on moduli space. Okay, so to do this, I want to define the notion of a quasi-conformal distance. So given two hyperbolic surfaces x and y, a map between them is K quasi-conformal if I simply take the eigenvalues at each point of df at each point. And I want their ratio to be bounded. Okay.
Is there a reason you want this and before you were taking Bell-Peterson?
Yeah. So there's a Weil-Peterson metric that gives rise to the volume form, but the metric is not complete and the curvature blows up to infinity, curvature blows up at the boundary. So it's easier to understand the Teichmuller metric as the genus of moduli space becomes large. Yeah. Okay, and now let me define the Teichmuller metric. The distance between 2 points, x and y on moduli space, which are hyperbolic surfaces, is given by half log k of the so I just take the minimal quasi-conformal map between x and y. And if you don't want to think about quasi-conformal maps, there is another geometric way to think about this, which is that instead of requiring this ratio to be bounded by k and k inverse, you simply require each one so if f satisfies this condition, it's bi-Lipschitz between the two hyperbolic metrics, k bi-Lipschitz between the two hyperbolic metrics. And then you can similarly define another metric and it will be equivalent to the Teichmuller metric. So roughly speaking, this is measuring how geometrically far apart the hyperbolic metrics of x and y are. Okay. Yeah, so now I can answer the question, but maybe this is also a good time to pause for questions. Okay. So let me write down a theorem that answers that question there, which is that if I have any one ball on moduli space, then the number of key triangulated genus G surfaces lying in that ball is at most c to the t. And here, c is a constant, like 10,000, that doesn't depend on t or g. And yeah.
How does this Teichmuller metric look at infinity where things develop long necks? So is there some picture of, because I have no idea what a ball of radius 1 means really, and how many there are.
Yeah, so ball of radius 1 means So like some constant greater than 1, like I can think of k, like taking k to be e or something like that. And I'm looking at this picture. I look at hyperbolic surfaces which are like e biliptids to each other in the hyperbolic metric.
But are there many balls of radius 1 which are really ball, which don't fall back on themselves?
Oh, you're asking about like the injectivity radius in moduli space.
Yes. For me, there is a central region and then things going toward infinity, and I wonder how big is the central region? So how many?
Right, so like the question is a ball like topologically a ball? I don't know. Yeah, I'm not sure. Okay. So
How many pounds about are there in this combinatorial set?
yeah, that's what I'm going to explain next. So so you can ask the question, how many T triangulated genus G surfaces are there? And this is kind of somewhat hard combinatorial question, but it's so there aren't exact asymptotics for this, but there's some non-asymptotic bound. So there are constants C1 and C2, so that this is true. And this was proved by Budzinski and Lu. And maybe it's also useful to think about how many balls do you need to cover moduli space. So to cover moduli space, you need infinitely many balls, but it's useful to consider the thick part of moduli space. And this consists of hyperbolic surfaces without a very short geodesic. And
You see, it's always assuming some proportionality between. In harding this, we assume T is about 4G always.
oh, this the top one?
Yes.
Yes, thank you. I forgot. Yes, so this is assuming.
Oh, equal.
Oh, sorry. Yeah,
yes,
fine.
yes. And the constant will depend on the constant implied into O.
No, this statement. I see. Yes. You can just maybe assume that G is greater than 4 plus epsilon times T, and then you'll get some usable constants there. Yeah. Okay, so let me say, so how many balls, type Miller 1 balls you need to cover the thick part of modular space? Yeah. So the point is that in this range, E equals OT, this is the remaining, like, so this basically is some sort of well distribution result. Range where T grows proportionally to T.
And again, the constant depend on what variables.
So, right. Yes. Cool. So in the, yeah, so let me explain what is the difficulty of to prove this theorem. Which is the following problem. Given two particular triangulations, are they close in MG? So if you want like an algorithm to determine if two particular triangulations are close in moduli space, that's very hard. So basically, you have to find a way of proving this without knowing how to do this. And so in the remaining time of the talk, I would like to explain the idea of how to resolve this problem.
Are two different triangulated things always different as bound in MG?
Sorry?
Can we have two triangulated surfaces which are combinatorially different but give the same bound in MG?
I mean, I think this is like, it depends on how exactly you formulate this question, but if you formulate this question correctly, I think the answer is unknown. Yeah. Also, by the way, something maybe it's a good point to mention that I forgot to mention earlier, is that, so fix a G and you take all the triangulated surfaces. This is the same as Riemann surfaces defined over Q bar. Bayes' theorem. And your question is like asking, given two Descent d'enfants, how do you determine what is the underlying Riemann surface? And that's kind of hard. Yeah. Okay. Cool. So the idea is to encode, try to encode triangulations using holomorphic one forms. By the way, this immediately shows that this is dense in MG in a topological sense. Okay. So let X be a Riemann surface. Let me explain what's a holomorphic one form. So it's a section of the canonical bundle, or locally, it can be written as f of y dy, where y is a local conformal coordinate and f is a holomorphic function. And away from the zeros, there exists a chart G where U is a neighborhood of F, such that omega is simply the pullback of this form dz. And now the point is that
Now I'm confused because a triangle can rotate 2 pi over 3, so I don't see how we have one natural one. Or is there a data I did not understand?
sorry. Oh, I have not explained so how to get this is a general statement about holomorphic one forms on a Riemann surface, not about triangulations.
Okay.
There will be an issue, yeah. Okay. But the point is that there is a geometric way to think about holomorphic one form, which is that you have a metric, which I'll denote by this. And this is simply gotten by pulling back the Euclidean metric. Okay. And you can patch those up to get a conformal flat metric. With singularities on X. And the singularities are going to be at the zeros of omega. So maybe it's useful to see an example. So take a regular octagon. So this is supposed to be a regular octagon. Okay. And glue, think of this as embedded in the complex plane, and glue opposite edges. So this edge will be glued to this edge will be glued to this edge, etc. And you'll get a genus 2 surface. But you won't just get a Riemann surface. You'll also get a flat metric on it, and a holomorphic one form on it. And the flat metric is simply going to be the Euclidean metric that you see here. And the holomorphic one form is simply going to be dz on C. And the zero of this is going to be at these points, which when you glue opposite edges together, you will get the same point. And that point will be a singularity of the metric. It will be the only singularity in this situation. Okay, so the upshot of this discussion is that there is a geometric way to view holomorphic one forms in terms of the flat metric that it is associated to. And in general, the holomorphic one form is like the flat metric plus some notion of direction. So if I want to know dz here, like I have to know the Euclidean metric, but I also know some form of like direction. dz gives me more. Okay. So there is a geometric way of thinking about holomorphic one forms, but there's also an algebraic way to think about holomorphic one forms, which is that it determines a cohomology class in this. And the cohomology class determines the holomorphic one form also. So in particular, omega holomorphic and cohomology 0 implies that omega is also 0. Cool. So what does all of this have to do with triangulations? Okay, so recall that we have this set com GT, and there's a map to moduli space, just a forgetful map. And now suppose you have a particular triangulated surface mapping to a particular point in moduli space. Then S determines a conformal flat metric with singularities, just because you consider the Euclidean metric on each triangle, and the singularities will be at vertices of S with degree not equal to 6. But this conformal flat metric with singularities may not necessarily come from a holomorphic one form. But it's useful to consider those that do. And so if it comes from holomorphic one form, then S, we will call S translational. And this comes from the term surface with the holomorphic one form is called a translation surface.
Does it mean you have some kind of coloring of the triangulated?
Yes, yes. So there's a combinatorial description involving like coloring system that will tell you, given a triangulation, if it comes from a holomorphic. Okay. Now, yeah, and in this situation, we will denote the holomorphic one form by phi sub S.
You have some choice.
Sorry?
You have some choice of multiplying by a third root of unity.
Yes, yes. That's right. So it's not uniquely defined. It's, yeah, but that's okay. Okay, so now let me try to explain how to get over the following, this difficulty. Okay, so let me write down this map again. And now suppose we have two surfaces in here, mapping to X and Y in moduli space, and assume that everything is translational. Then I have the following claim. If X equals Y and phi S equals PR, then R and S are the same triangulation. Why is this true? So this board tells us that the cohomology determines the form. So this means that PS equals PR. And now what I claim is that you can rebuild the triangulation S from Ts. How can I rebuild? So I start with a 0 of yes, and this has to be a vertex of S. Recall that the zeros of a holomorphic one form are the places where the corresponding conformal flat metric is singular. And away from vertices, a triangulation looks flat, obviously. So if you have a 0, it has to be a vertex of the triangulation. But you also know the flat metric corresponding to S. So suppose you want to build a triangulation and you know the metric and you know a vertex, but then you also have a sense of direction. Yeah. So I know where to start the edges. So I start from my vertex and then I am trying to build, but I know exactly where the edges have to be. And then like I know I go travel for distance 1, and then I know where the next vertex is, and I can continue this process. Okay. So yeah.
If you only had the flat metric,
Mhm.
what other, like, could you recover more triangulations? Like, would it be not unique?
Possibly not. Yeah, because a priori I wouldn't know like where
The orientation of the triangle?
Oh, sorry, if I have the flat metric. You mean I don't know which
I
direction
have
to
like
go?
absolute value of ds instead of ds.
Right, okay. So I would still get a vertex to start from, but maybe I wouldn't know which direction to go. But it's possible that like the yeah, it's not clear to me if you can have multiple very different looking triangulations with the same flat metric. But of course, this building process doesn't work.
I was confused about something else.
Yeah.
So the triangulation is just data of triangles glued together.
Mhm.
How do you get a complex structure from this?
Oh, yeah, so you get a complex structure on each triangle. It's preserved by,
What is the complex structure of each triangle?
yeah, it's just a unit equilateral triangle
In C.
in C.
Then you have singularities at the vertices.
Yeah, that's fine. You just extend, I mean, you have like Riemann removable singularities there.
Okay, so I have to apply some singularity removal.
Yeah, but it's like elementary, I mean, yeah.
Okay, but I wasn't told.
Oh, okay, sorry. Yeah, so it's just a discrete set of points. So
Okay.
yeah, it's fine.
Yeah.
So you like a priori you get a Riemann surface with a discrete set of points removed, but there's a unique way to put those discrete set of points back in.
Yeah, for me, it's like you take ideal triangles in hyperbolic space.
Yes.
And then you only glue.
Yes, that's exactly the same. You get exactly the same result. Okay. Right. So now the point is that you don't just have this statement here, but actually one can prove a quantitative version of it. Which is that if instead of x being equal to y, you have x, y are close in moduli space. Instead of phi s being equal to phi r, you have that phi s and phi r are close in cohomology for some reasonable definition. Then you don't have that s and r are the same, but you have that s and r, I'm going to say, look similar, which means that, I mean, so this is a triangulation, this is another triangulation, and they're like the same triangulation on most of the surface, but they could be different on like some of the surface. And so the point is that there was this difficulty that given two particular triangulations, I didn't know how to tell whether they are close in moduli space. But the point is, if your triangulations are translational, and yeah, so for instance, maybe I wanted to say there that if I have two triangulations and they're close in moduli space, then the triangulations themselves are combinatorially close in some sense. And I don't have that, but if they're translational and also the cohomology classes are close in cohomology, then I do have such a statement that the triangulations themselves look similar. And so that's how to resolve the difficulty. And then to actually prove the theorem, you have to remove these assumptions of translational and everything. But I won't talk about that. I will end here.
Thank you very much. Other questions?
So here you use one form. Is it possible to avoid this problem of translational to use section of the third tensor power of one bundle of one form?
Yeah. So you want, so if you have a triangulation, you'll get a sextic differential. But the thing is, it will not be holomorphic even. It will be like meromorphic with poles of up to order 5, because you can have degree 1, 2, 3, or 4, or 5 vertices. But the point is that after passing to a 6-degree branched cover, you can take the 6th root of this sextic differential, and you get a 1. So that's actually how you remove this assumption.
Any other question? Okay, so let's thank our speaker again for this nice talk. This was the last member colloquium for the semester. So